All right, everybody. Welcome to the last lecture of the semester on elliptic curve cryptography. Um, just as a reminder, this is the last day of new stuff. Check out Canvas for Dr. Hassanian's office hours, and Dr. Hassanian should be um, in class, or someone should be in class um, during our regularly scheduled class times to let you take quizzes, to help you out with homework, projects, whatever you need help with. So that's that. Um, so if you have any questions, feel free to reach out to me via email. Again, I'll answer as quickly as possible, but it also would probably be beneficial to go to Dr. Hassanian's office hours, which I will post in Canvas. Okay. All right, so last time we talked about elliptic curve Diffie-Hellman, and if you recall, when we developed Diffie-Hellman for just finite fields FP, on top of that we built the El-Gamal crypto system, and the El-Gamal crypto system is secure for large prime numbers P because the discrete logarithm problem is difficult to solve. Okay. But how, so we have this Diffie-Hellman key exchange for elliptic curves now. So how do we use that with Elgamal for elliptic curves? So let's say Alice and Bob want to communicate, and Bob wants to send the message comment, for instance. Um, how does he encode that? When we wanted to encode a message over, when we were doing stuff just mod P, the very first thing we needed to do was encode a message using numbers from FP. And the thing that for a long time, I kind of swept that under the rug. And then recently we said, you can do this special blocking thing where you encrypt or encode rather each letter as a three-digit number, and then jam all those numbers together, and then encrypt that as one message to send off. Okay, with elliptic curves, we're going to uh, not do this blocking thing because elliptic curves are a little bit weird. One thing you might say, is, well, let's try changing every letter to a number and then just using every number that we get as like the x coordinate of a point on the elliptic curve E of FP. The problem with that is that if you give me a number in FP, there is no guarantee that M is the x coordinate of some point in E of FP, depending on the elliptic curve. So that's kind of an issue even with the blocking idea. Maybe each number that we come up with, and maybe each number is the x coordinate of a point on an elliptic curve. But then when we gem them all together, that number is not a point on the elliptic curve, or the x coordinate of a point on an elliptic curve. So for elliptic curve cryptography, you do kind of encode each letter separately, and then we're going to send them all off one by one using different keys is the idea. But how do I even encode the letter C if 3, for instance, ABC, if 3 is not the x coordinate of a point on the elliptic curve we're working with? And the answer is pretty straightforward. It's just, well, hey, let's, instead of just saying C is 3, because we're working with prime numbers that are still relatively big, we're working with prime numbers that are about 256 bits, which means about 77 digits long. We can say, instead of A corresponding just to the number 1, let's let A correspond to any number between 1 and like 10,000, for instance. And even that is like way bigger than we need. Even if I just said let's let A be correspond to any number between 1 and 10, that's usually enough space for us to find some number that will correspond to that letter. Okay, so what we normally do is we say, let A represent be represented by any point on the curve that has an x coordinate that's between 1 and 10,000. And then B can be any point on the curve that has an x coordinate between 10,000 and 1 and 20,000, for instance. Okay. Then to encrypt Comet, I just need to find some point with an x coordinate between 20,000 and 1 and 30,000, right? That sort of corresponds to, so if A is that first range, B is that second range, C would be the next range of 10,000 numbers. And from the point of view of probability, I haven't gotten into the weeds about like how many points there are on an elliptic curve. From the point of view of probability, you're basically guaranteed that you'll find a point that satisfies the conditions that you need. So let me switch to Sage really quick for a second and show you how that works out. So here I've generated a prime number p that is actually really, really, really small in relation to modern cryptographic methods. So we've got p is this number 275,881, and I got that just from the SMPY next prime again. As a reminder, Sage is kind of built on, Sage is really built on top of several different things, Python being one of them. So any Python code you type in should work in Sage. Okay, and then we're looking at the elliptic curve over that finite field FP for P is 275,881, with the coefficients A and B being -3 and 1039. Okay, and so to see if the x coordinate that we want is between, to see if there is a point on the elliptic curve with a given x coordinate, I can do the following. I can do E dot is x coord, and I can see, does this elliptic curve have any points with an x coordinate of 0? Okay, so let's see there. I ask, does it have any x coordinates with point 0? And it says no. Okay, what about 1? And it tells me false. What about 2? Oh, 2, yes. So if I'm, searching for any number between 0 and 10,000, really, I can just say like between 0 and 9, to serve as the letter A, then I could take a point on the elliptic curve that has the x coordinate of 2. And actually, I can ask Sage again to give me that point by doing, once I know that x coordinate of 2 exists, I can say E dot lift x 2, and it will tell me the point on the elliptic curve that has that x coordinate. Okay, so the point 2 comma 29,596 is on this elliptic curve, for instance. Okay, and I can do the same thing with A could be given by 2. And again, all this stuff about encoding is just public information that Alice and Bob can say to each other out loud. That's fine for them to say to each other. The only thing that they are not going to want to say out loud is their private keys. Okay, but actual encoding protocol is totally public information. Okay, so 2 could serve as A. Actually, this point right here could serve as A, and then I need to move on and find another point that could serve as B. Well, apparently there's an x coordinate of 3, so I could say, E dot lift x 3. I could say that the point 3, 89,987, that's going to serve as my letter B, and so on and so on and so on. So it's a little bit more annoying to do the actual encoding part of this, but it is still pretty straightforward. Just basically do a search and find all of the points that you want. Or again, say any number between 0 and 10 as my x coordinate. That's going to serve as A. Any point that has a x coordinate between 11 and 20, that's going to serve as my letter B, and so on and so on and so on. So as far as encoding, that's not really something that we need to worry about. We'll just follow this scheme of just letting A correspond to a range of x coordinates, B corresponds to a range of x coordinates, and so on and so on. So Alice and Bob have agreed on a public, in public on a message encoding protocol. Okay, so now they want to know, how does Bob send Alice a message? So let's say that Bob wants to send Alice a single number, and really a single point, and that's going to be a point with the x coordinate of 19. So the x coordinate is sort of always serving as sort of the message that we're sending. Okay, so in Sage, so we're using that same example, this elliptic curve. So in Sage, the message that Bob wants to actually send him is going to be the elliptic curve point, so E dot lift X, and I checked that 19 works before this. So Bob wants to send this message. Print M. This is the point Bob wants to send Alice. 19, comma, 122,172. Now again, Alice gets this message and understands that, hey, I only care about the X coordinate. And again, that's publicly available information. It's okay for them to say that part in public. Okay, so Alice, or Bob wants to send Alice really the message 19, comma, 122,172. Okay. All right. So Elgamal on elliptic curves is going to work exactly the same as Elgamal over finite fields in theory. Okay, so Alice wants Bob to send her a message. They publicly agree to this elliptic curve. The y squared equals x cubed minus 3x plus 1039. That's the elliptic curve that I have in Sage right now. Okay, with the prime number 275881. That's the prime number that I have in Sage right now. Okay. And they also agree to a generator, that you do need a generator of this EFP. So you want an elliptic field, or sorry, an elliptic curve that has a single generator. So let me go into Sage and show you what that generator looks like. Let's do um, print e.gens. When I print that e.gens, we get this. This is our generator. Okay, so I'm going to call P E. There's two things you can do. I can do e.gens. That's, you notice that's a tuple. I can ask for the first entry. It's a tuple with an empty second entry, so I could ask for the first entry by doing that. And then I could say, make sure that I'm actually looking at what I want to look at. And there we go. We've printed P. All right, so we've got our generator and we've got our message that we want to send. Now, what does Alice do to receive a message? In order to receive a message, just like in Elgamal beforehand, Alice needs to do her part in the Diffie-Hellman key exchange. She chooses a random private key, A, and sends Bob the public key, Q, which is A times the point P. Okay, so let's go to Sage and see this. Okay, so Alice computes Q, which is, so let's say she wants the secret key, her secret key to be this number, 40,873. She computes A times P. Here is the public key that she sends to Bob, and generally anyone she wants to communicate with. 27,065, 239,232. All right. What does Bob do once he receives that information? Well, think back to Elgamal just over FP. Bob had to do his part of the Diffie-Hellman key exchange. That was one part of the message he sends back. So Bob's going to compute his part of the Diffie-Hellman key exchange. I'm going to call that R. He's going to come up with a random secret key as well, 1919. And Bob computes B times P. This is his part of the Diffie-Hellman key exchange. So show me R, please. So he sends, one part of the message he sends Alice is this 110,002, comma 102,818. And then Bob also needs to compute the shared secret key. So to compute that shared secret key, the shared secret key is going to be A times B times P. So he has in his possession from Alice A times P. What's the only thing he can do with that? Multiply it by B to get A times B times P. Okay, so the shared secret key S is going to be B times Q, which is A times P. Print S, please. Okay, so the bottom line is the shared secret key. And once he has that, in our group that only has the one operation of addition, what can he do to get his encrypted message? Well, he can take the shared secret key and add it to, oh no, Chase. This is a good place to use some whiteout because I wrote down the wrong point. he can take the shared secret key and add it to the message that he wants to send, S plus M. Okay. Now again, this addition operation, you might say, S plus M, that's so easy to undo, like I could just brute force it. But the addition operation is really weird on an elliptic curve, right? So that's what he computes. And then Bob sends Alice the 2 points, R, which is his part of the Diffie-Hellman key exchange, and then the encrypted message, which is the point in E of FP. Okay, so let's look at what Bob sends. Bob sends the point R, and then the message he actually computes, I'll call it EM, is, well, S just plus M. Print R, print EM. This is what Bob sends, the last two lines of the output here. This is what Bob sends to Alice. The first line is his part of the Diffie-Hellman key exchange. The second line is the encrypted message. Now, let's think about, oh, sorry, there we go. I forgot to switch to Chrome. First part is the shared, or sorry, not the shared secret key. His part of the Diffie-Hellman key exchange, his public key. And then this part is the encrypted message. Now, let's think about what Alice does to decrypt this. So Alice receives from Bob, R, which she knows is his private key times the generator, P, and then the encrypted message, which is the shared secret key plus M. So in order to decrypt this, Alice just needs to get to the shared secret key. The way she does this is she computes A times what Bob sends her. She has B times P. She wants A times B times P, so she'll do A times that first part of the message that Bob sends her, that public key, which gives gives her A times B times P, which is the shared secret key. So let's go look at that in Sage and make sure she gets the same thing that Bob got. S, I'll call it SA for S Alice. She computes A times R. And so we're going to print what Bob computed S and what Alice computed. And they got the same shared secret key. And so now what does Alice do to decrypt the message? Well, now she has S, so the encrypted message is, well, she'll take the encrypted message and subtract the shared secret key, where again, subtraction is defined by this weird group operation on elliptic curves, which is just M. Okay, so let's go make sure she gets what she needs to here. So final message, she takes what Bob sent her, the second part of what Bob sent her, which was EM, and she subtracts the shared secret key that she computed, and she gets, oh, I gotta print it. She gets 19, comma, who cares? Again, the Elgamal encryption system, we only really care about the X coordinate. So she got back the message that Bob originally wanted to send, which was the number 19, which he then encoded as a point on the elliptic curve. Okay. And that's how encryption with Elgamal on elliptic curves is done. Okay. If Bob wants to send a more complicated message than just a single number, if he wants to send a word, then he encodes every letter, as we talked about above, by saying A corresponds to a range of X coordinates, so that he's always able to pick something on the curve. B corresponds to a range, and so on and so on and so on. And then Bob encrypts each letter, each point, then separately with different private keys. So he does need to encrypt each point with a different private key each time, because if he uses the same private key, then it makes it easy for an eavesdropper to break this. But if he uses a different private key for each part of the message, then he'll end up sending Alice essentially, a message that's just like before, twice as long. Each letter will have a public key and the encrypted letter, and then same thing. The next one will have a different public key because he's using a different private key, and then a different points, and so on, so on, so on. Okay. And that's how Elgamal is done on elliptic curves. And this is implemented again on most modern websites. If you check the certificate, the security certificate, most modern websites are using a version of elliptic curve cryptography. One of the most common ones, again, is that curve 25519. That is pretty commonly used. And that one, a weird thing about that one is that a generator that's used for that uses the base x coordinate of 9. And that actually doesn't generate the entire elliptic curve. And so there's, again, just like with RSA, the textbook versions of RSA and Elgamal, there are modifications and variations on these things that people have done to make them more secure and harder to break that I'm not getting into. But if you want to dive into those things, I would highly encourage you to do that. So that's it. That's all for the semester. Thank you all so much for a great semester. If you have any questions, feel free to email me. Um, and don't forget about Dr. Hessinian's office hours, and she should be there as well during the regular class times to answer questions and let you take quizzes and work on homework and stuff. So rest of class time is for work. Watch all these videos outside of class. Okay. Thank you all. Have a great rest of the semester. Good luck in your other classes. And to those of you who are graduating, congratulations, and have a great career once you leave SU.